And I think we're here. So let's begin. Welcome, everyone. This is week 3 of our course on our universe, the known and the unknown. And we have this nice picture from the James Webb Space Telescope. Actually, the picture isn't so great, but the data is very important. And what you see here, oops, something, okay, this went away. Oh boy, did I hit the wrong button? There it goes. Let's see if that works out. Okay, so there was a press release on the 20th of November by NASA announcing that the James Webb Space Telescope had discovered a galaxy that was observed when the universe was 350 million years after the Big Bang. And they didn't provide much science information in the press release, but I searched the web and was able to find the original scientific paper, which was actually published near the end of July. So I don't know why they waited so long. But this is the key data from the paper. And at various wavelengths, they see nothing over here, but at these wavelengths, they do see this galaxy. Here's an enlargement of the last frame. There's the galaxy. Not terribly impressive, big white splotch, but the spectral analysis, in other words, you look at the wavelengths of light that are coming toward us from that distant galaxy. And as we'll discuss today, you can tell by the wavelengths how far away that galaxy is. More specifically, you can tell how much smaller the universe was in size when that light was emitted. And the number that they measured is the so-called redshift. Z is 12.5, which is the largest redshift of any reported galaxy that I'm aware of. And that means that the universe was 13.5 times smaller in size then than it is today. And if you assume the standard model of cosmology, then you find out that, oh, this is going to, yeah. Then you find out that that means from the theoretical calculation that the light was emitted 350 million years after the Big Bang. And the topic that we'll talk about today has a lot to do with this, so we'll be able to understand in more detail what all of this really means. But this is a remarkably sharp peak and if you look at that, this is all blurred out, but if you look at the paper, then you find out that this sharp peak is at a Z of 12.5. which is the key element in the discovery. So today we're going to talk about the most difficult challenge that astronomers have faced historically and continuing to today, and the challenge that, if met, reveals the greatest discoveries. And that is the need to measure how far away everything that we see in the sky is. So measuring cosmic distances is the challenge that astronomers have struggled with for centuries and made good progress in the 20th century. And that good progress led immediately to what I would say is the greatest discovery in the history of astronomy. And that's what we'll talk about today. So we're going to start with a discussion of how we analyze the spectrum of light that comes from atoms and of the atoms that are emitting light in remote objects in the sky, and how we compare those spectra to the light that we see in our laboratory. and use that information to determine distance. Then we'll talk about the other techniques that are involved in measuring the distances to the very remote objects in the universe. And finally, that will lead us to discussion of the greatest discovery in the history of astronomy, and that is that the universe is expanding and therefore had a beginning. And those are two remarkable features of our universe that you just can't see by looking in a normal way through a telescope at the heavens, because nothing in the universe seems to change on a human timescale. And so it appeared for centuries, as people often said, that the universe always was and always will be as it is today. And that turned out to be completely wrong. Okay, so that's the agenda. The first topic is we need to understand in some detail what is light. And this goes back centuries. It took centuries for a physicist to understand the true nature of light, about 3 centuries, in fact. And by the year 1900, physicists thought they knew everything that was important to know about nature. Boy, were they wrong. And in the year 1900, physicists divided all of the contents of the universe, all the entities of the universe, into 2 categories, which were absolutely distinct and separate from one another, with no cross migration in between, no crossing this great wall that separated the 2 classes of entities. And these 2 classes were the particles, which made up all the things of the universe, and the waves, which were an entirely different class. So the particles had these various characteristics. They could travel through empty space. They didn't need any medium to travel through. Particles came in integer numbers, like little baseballs, and you could always tell where a particle was. You just had to look. And particles didn't do any funny stuff like diffraction and interference, which waves did. So waves were viewed as not a thing in and of themselves, but the motion of other things. So a sound wave is the motion of air molecules, the organized motion of air molecules. Ocean wave is the organized motion of the water molecules that make up the ocean. And they don't come in integer quantities, they come in a continuous amount. So you don't ask how many particles are in a wave, you ask what is the height of the wave, or what's the width of the wave, or some other continuous measurement. And waves aren't localized, they spread out through all the available space, and they have these behaviors that are very strange from a particle standpoint, and these are called diffraction and interference. And because light clearly displayed diffraction and interference, it was deemed universally accepted that light was on the wave side of the Great Wall. This is diffraction. If you have a barrier, this yellow barrier with a hole, then an incoming wave, the crests of the waves are white, the troughs of the waves are black. An incoming wave, some of the wave would make it through the hole, and it would create this enormously complicated pattern on the other side. You see there's a central lobe where most of the energy is, and then there are these dead zones which separate minor lobes. And there's another dead zone and another minor lobe and another dead zone and another minor lobe. And in fact, there's an infinite number of these minor lobes, each separated by a dead zone. And by that, I mean, along this gray area, there is no wave energy at all. So there's high wave energy, then it goes to zero, then it goes to up again, but not to as large a number as the center, and so on and so on. So it's really quite complicated, much more complicated than if this was a particle. If a particle makes it through a hole in a barrier, it just continues on a perfectly straight line forever, and doesn't do any of this funny stuff. And if that hasn't convinced you that particle waves are different, then these are the equations of motions in the absence of any force of a particle versus a wave. So if there's no force, then Newton's law, F equals ma. If the force is zero, then the acceleration a is zero. So the particle continues on its the velocity that it started with indefinitely. Waves, on the other hand, can't be still. Waves are motion, and the motion of other things. But the wave is the organized motion, and this is the equation for that. So there's a component of time. The wave is changing in time, and the wave is changing as it goes through this three-dimensional space, X, Y, Z. That's, if you don't like math, then you're certainly not going to like that equation because it's long and complicated. But one should never fear these big equations because they're really pussycats. They say typically they say something very simple. And in this case, this equation says the primary consequence of this equation is that waves are smooth. So waves gradually go up and down and gradually go up and down again. They have no jumps, no discontinuous changes in the amplitude of the wave, and they have no kinks, which would be discontinuous changes in the slope of the wave. So the slope changes gradually, the amplitude changes gradually, the height changes gradually. And that's what the equation says. Okay, this is interference, which is related to diffraction, but slightly different. Here we have two sources, and the waves coming from the two sources interfere, and they make this very complicated pattern. And if you had a piece of film over here, what you'd see is high light intensity and separated by these black fringes, which are zero light intensity, and then high and zero and zero and high and zero and so on, all the way across the film. This is called interference. And this is a remarkable property that no self-respecting particle could do. If you had a little, let's say, a machine gun shooting bullets from point A and a machine gun shooting bullets from point B, then the bullets would spray all over and they would cover the entire range. There would be bullets everywhere on the film. And there would be no areas in which there were absolutely zero bullets. The bullets from B don't care about what's happening with the bullets from A, and so you just get the sum of the two, and the sum of the two is never going to be zero. But with waves, the sum of two waves can indeed be zero. So waves are really quite different in their behavior. And this is the wave of a boat on a very calm set of coastal water. And you see that this very complex pattern comes from the first boat, similar pattern from the second boat. And as the boats move through the water, this entire pattern moves with the boat as if it was a single solid object. Of course, it isn't. It's the behavior of trillions and trillions of water molecules, but all of those trillions and trillions of molecules are doing exactly what they're supposed to do all the time to make this pattern. And that is really remarkable if you think about how does this little water molecule over here know when it's supposed to go up and down? But it does. So the key litmus test for determining whether something is a particle or a wave is called the two-slit experiment. This is the same thing as what we saw before. You have two sources. In the previous slide, they were labeled A and B. And the two sources create waves if this is a wave coming in. And the two new waves interfere with one another. And sometimes they make a very bright line, and sometimes with high energy, and sometimes they make no line at all with absolutely zero energy. And this alternating pattern there is called a fringe pattern. So whenever we see something making a fringe pattern, we know it's a wave. At least all of this was the concept of physics in the year 1900.
Robert,
Yes.
I'm just curious, can understand when you can see a wave in water stopping and what appears to stop it, or at least the energy that projected it to stop. But what about in space, like waves that are heading out, like we're out to whatever it was, 350 miles short of the Big Bang? Are those waves still moving?
Those are light waves, and they are light is always in motion. Yes.
So beyond the 350 miles, if you were able to see there, they would continue to be heading out, and in red light fashion.
I'm not sure that I fully understand the question, because the 350 was 350 million years after the Big Bang. So,
Right.
yeah, it wasn't miles. It was 350 million years. That's the point of time, the instant of time in which the light was originally emitted by this galaxy. And that light is arriving at our telescope today.
Got it.
So it took all of that time to cross the universe and get to our telescopes. And the whole way, something was waving. Some part of the light, and we'll talk about what it is, some part of the light is continuously waving, trillions of times per second, very high frequency light.
But the light that was emitted from there to begin with, to make that come back to us, is moving outward as well?
Yes, we presume that light is moving out in every direction. We only see the light that hits Earth, but from what we know about other things, a light is typically emitted by most objects in all directions equally. There are few objects that emit light in concentrated beams, like quasars, but those are exceptions. Those are very rare exceptions and very interesting exceptions, but that's not what a typical star does, and that's not what a typical galaxy composed of typical stars does. The light from those objects goes everywhere. And I should say again that that's what we believe. We can't prove that, because we only get to observe the universe from the vicinity of Earth. I mean, we can put a satellite in space, but it's only a couple 100 miles above the surface. So it's really, we have a very limited vantage point.
So quick question, if I may.
Andrew.
Good morning. So the grid pattern, which was displayed, which you showed, based upon the interference from the two sources, well, one source diffracted, resulting in that grid pattern.
Yeah. That one?
Right. So if I sit here and I'm at Earth looking out, if there was only one light source in the universe, I would see a wave coming at me. But why, just one of the things I've thought about, but never quite understood. If I'm sitting here at point A on the Earth, and I'm looking out and there's these untold number of stars,
Yeah.
why aren't we seeing extraordinarily complex grid patterns?
Well, I don't know if I have the picture here, but to get this interference pattern, the light from A and the light from B have to have precisely the same frequency. And they have to have a precise relationship in the phase of the wave. So when the wave at A is cresting, the wave at B also has to crest. And then they go up and down together in complete synchrony. Then you get an interference pattern. If you have a different frequency at A and B, then A will go up and down fast and B will go up and down slower, and then the interference pattern gets washed out. It's just, you don't get an interference pattern.
So with all these sources of light in our universe,
Yeah.
I would think that there is going to be interference because somebody's signal will be at the same frequency. Why is that not true?
Because the frequency spectrum is an immensely large number. We can measure differences in frequencies to 18 decimal digits. Nature measures frequency differences to much better than that. And there are not 18 digits worth of stars in the universe.
Okay.
The number of stars in the universe is about 12 digits.
Okay, so we're able, okay, super. Thank you.
It's easier to talk about digits than what the number is because those numbers don't have names. They're too big. Okay, so I think we were here. And I love the questions because, you know, I've heard this talk before, and no surprise. And the most interesting part for me is when there's something new coming around, and that's the questions. So please feel free to continue to ask. Okay, so this is the pattern that we know and love that we get when the illuminating source is a wave. And if the illuminating source was a bunch of particles, then you'd think you get a smear of particles over here projecting through this hole, and a smear of particles on the other side projecting through that hole. And you know, you'd have two blobs, let's say. That's what you'd expect if you illuminated this with particles instead of waves. So Dr. Tomomura, Akira Tomomura of Hitachi Corporation did the experiment with electrons. And what the background story is, in something like 1962, Richard Feynman gave a lecture and he talked about interference. And he said, wouldn't it be marvelous if we could do this experiment with electrons and show whether or not electrons are really particles or really waves? but it's way too difficult and no one's ever going to be able to figure out how to do that experiment with electrons. Well, when one of the world's leading theorists tells experimental physicists they can't do something, that's like waving a red flag in front of a bull. So all these experimental physicists devoted their careers to trying to do this experiment, and several succeeded. Dr. Tomomura wasn't the first, but he came up with a much more convincing set of data than his predecessors. And I'm going to show you the data. So what he did was he arranged a source of electrons that was a very low energy electron. So it had a large wavelength, relatively speaking. So he could make the slits of the appropriate size. And he arranged it so that only one electron was in the machine at a given time. And instead of using film, he used some sort of sensitive material. So when the electrons came through the machine, if there were particles, they would go through only one hole and make a blob, participate in the blob over here, or go through the other hole and participate in the blob over here. And so this is what he saw with the first 200 electrons. And what you see here is that it looks like each electron has hit a single point on the screen. And there's not much of a pattern, so it sort of looks like a somewhat random distribution of electrons. And this is not what a wave does, right? A wave that hits the ocean, an ocean wave that hits the shore doesn't hit a single grain of sand, it hits the whole beach. So you're not going to get a single point illuminated on the screen if the particle is a wave. So the fact that they're single points proves that these electrons are particles. But when he ran 140,000 electrons through the machine, one at a time, he got the interference patterns, the fringe patterns. Now, these aren't as crisp as with light because this is a much more difficult experiment. This is the experiment that Feynman imagined no one would ever be able to do. And so the electrons are sensitive to all sorts of stray fields, and so they smear around a little bit uncontrollably, but there's clearly an alternating pattern of high intensity exposure and lower intensity exposure. And that proves the electrons are waves. The bottom picture proves the electrons are particles. The top picture proves the electrons are waves, and they're the same electrons. And since there's only one electron going through the machine at a time, the only conclusion that one can come to is that the electron went through both slits simultaneously, creating electron waves that interfered on the screen. If each electron went through only one hole, you wouldn't have an interference pattern. You'd have two splotches. That's not what that's not the way nature behaves. Nature actually shows you that electrons have wave behavior and simultaneously they have particle behavior. And that is what Einstein established in 1905. And this is from, I think, 1970 something. So it took an awful long time for the data to come that verified the proposal of Einstein and de Broglie from the early part of the 20th century. And that proposal was that is called particle wave duality. And it's a fundamental principle of quantum mechanics. And particle wave duality says that everything in nature has simultaneously both particle properties and wave properties. And some things sometimes seem to be more particle-ish, and other things seem to be more wave-ish, but everything has both sets of properties to some degree all the time. and depending on the circumstances of the environment. And light in particular is both a particle and a wave. Two things that were considered absolutely distinct, separate, with no commonality. And when Einstein first said it in 1905, this was like heresy. I mean, you were challenging one of the fundamental beliefs of physics. He continued to onward and challenged almost all of the fundamental beliefs of physics. And people fought him tooth and nail all the way. But all of the things he said in 1905 turned out to be exactly correct.
Robert,
Yeah, go.
I'm curious, was he able, or was anybody else able to tell where the in-between number was between the 200 and the 140K, and what that would look like when the particles were on the verge of becoming waves? What does it look like?
Yeah. No, actually, every one of these particles, including the first 200, is a particle and a wave. Every single one. Now, when they hit the film, they interact at a single point. That's the particle-ish nature of them. And that's true here too. You see, these are really made of dots, right?
Mm-hmm.
Just like here. Now, if you blur your eye a little bit, there's a concentration of electrons here. There's a concentration here. If you try hard, you can sort of see a fringe pattern down here, but it's not very distinct. It looks like just random stuff, but actually there's more here, and there's more here, and there's more here, and so on. So the fringe pattern is there, it's just not evident because it's too weak a signal. These electrons are not different than these electrons. They're all the same. It's just a question of not being able to see the pattern without more data.
And if you looked in between, there would be more of a fringe pattern as you headed up.
Right.
Okay.
The more and more electrons you have, then the more of a pattern you see.
Got it.
I mean, you can sort of imagine that if you take a photograph and you take a photograph for a millionth of a second, you're not going to get a lot of light, and you're not going to see all the detail that you see in a photograph that takes a tenth of a second. Did I make any sense there?
It's sort of like if you look at the wave of water and you look at the first part of the wave, it might look like the bottom frame. And then if you continue on, it would look more like the top frame.
Yeah. I mean, if you look at it at a single molecule in an ocean wave, you're not going to see the wave pattern.
Got it.
Yeah. It's there. The molecule is doing the right thing to participate in the wave in a constructive way, but it would be hard to figure it out looking at just one molecule at a time. Well, this is a mind-boggling statement here. I mean, if it hasn't confused you, then I haven't explained it well. Because, you know, this is something that 99% of physicists of the year 1900 never accepted. I mean, they went to their grave not believing it, despite all the evidence. I mean, it just was so earth-shatteringly different that most of the physicists couldn't adapt. Max Planck once said, you can't convince old scientists of new theories. You just have to wait for them to die. Okay, so let's go on. And now that we have established that electrons and other particles also have wave characteristics, let's talk about how this impacts the light that we see from the universe. So imagine that we have a single atom, which has a nucleus where all the protons are, and so this is the positive charge. The electrons have a negative charge, so having opposite charges, they're electrically attracted to the nucleus, and so they spiral around in orbits around the nucleus in some complicated ways, but let's just assume things are simple. So we're talking about one electron that's orbiting at this radius. So I drew a band instead of a line because I'm going to do something with the band. And I imagine that I cut the band here and I stretch it out on a straight line. So this is the orbit. And the orbit starts at A and it goes around, B's in the middle, and it comes back to A. So it starts at A and it goes around to B and then it ends up at A. This is something like a map of the Earth that's flat. And if you see a map of the Earth on a sheet of paper, it's usually cut at the international date line because there's not so much land on the international date line. And this would be go through this B would go through Greenwich, England, which is the origin of our coordinate system. So the electron would go around the orbit and it would end up at A again. And what it does at A has to be the same as what it did at A on this side, because A is indeed the same on both ends. So if you have an island on the international date line, it better show up on both sides identically because it's the same island. So let's imagine that we have this electron is a wave, as we demonstrated before. It has wave properties, so it has a wavelength, so it oscillates, something oscillates up and down. And this is a possible situation, except that it doesn't fit the wave equation because the wave is sort of at a minimum here and it's at a maximum there. And that's bad because this is the same point as this. And so this is a discontinuous change in the height of the wave, and the wave equation doesn't allow that. The wave equation says the wave has to be smooth. It can't have any discontinuous jumps in the height, and it can't have any discontinuous changes in the slope. No kinks, no jumps. So this is not a valid solution to the wave equation for the orbit of this electron, because this requires a discontinuous jump at one point. In fact, the only way that you can get an acceptable solution to the wave equation for a circular orbit is that if the value at one side, the A side, is the same as the value when you go around and you get back to the original point. So the value has to be the same and the slope has to be the same. And the only way you're going to get that with a sinusoidal curve like this is if there is an exact integer number of wavelengths around the circumference of the orbit. So this is one wavelength, two wavelengths, 3, 4, 5, 6. You can't have 6.5, you can't have 6.7, you can't have pi wavelengths. You can only have integer number of wavelengths. And if you don't satisfy the wave equation. So it can't be a wave. So anything like this is ruled out, and only these are acceptable. Only when the circumference of the orbit is an integer number of wavelengths, lambda is the wavelength, then you have a valid orbit. Any questions about that? This is the heart of quantum mechanics, that you can't have just any energy, you have to have the right energy, the right frequency, the right wavelength. Okay, so this means that electrons orbit the nucleus of atoms in a very different way than planets orbit stars. So for electrons, the wavelengths are very small, and the structure of the atom is very small, and you have a series of shells. The electrons occupy these shells and nowhere else. The electrons can be in the first shell, the second shell, the third shell. The first shell is one wavelength all the way around. This is two wavelengths around, this is three, and they can never be anywhere in between. There's no such thing as the 2.5 shell, because that would be inconsistent with the wave equation. So there are a certain number of electrons that can occupy this orbit, a certain number in this orbit, and so on. And they can't get any closer because one is the smallest integer in terms of the wavelength of the electron. If it had 0 times the wavelength, you wouldn't have an electron. So the minimum number you can have is 1. And so it can't get any closer. And that means the atom can't collapse, which is a really good thing. Because if the electrons could collapse into the nucleus, then atoms would be 100,000 times smaller in width than they actually are, which means that the Earth would be a couple miles across. And you can imagine what the density would be, and there would be no life. Things just would be completely inert. So these electrons have to occupy specific orbits. Now, every element on the periodic table has a different nuclear charge, a different number of protons, and so the orbits are different for each type of element on the periodic table. And there are different radii and different patterns and so forth. And so this structure is different for every element on the periodic table. And if you make a plot of the energy, then the energy of orbit 1 is it's the closest to the nucleus, so has the highest binding energy, which means it has the most negative energy. If it had positive energy, it wouldn't orbit the atom. So it's bound in the atom because its energy is less than 0. And the energy of the second orbit is up here. The energy of the third orbit is up here. 0 is somewhere up here. And all of the orbits lie in the negative range of energy, all below 0. Now, if you have electrons that are populating these different orbits, then it's possible that one of them might fall from orbit 2 to orbit 1. That's closer to the nucleus, so it's more favorable to be in orbit 1 if there's room for it to enter. And so if the electron does transfer from orbit 2 to orbit 1, then it has to get rid of this energy difference. It's got too much energy to be in orbit 1, so it's got to get rid of this excess energy, and it does so by emitting a photon of light. That's how atoms emit light. The electrons move from one orbit to the next. And so you get a single photon being emitted, and the energy of that photon has to be exactly right. Energy is conserved, so the energy of if the electron loses energy, then the photon has to carry away that energy so that the total energy of the universe is constant. So the energy of the photon, which is Planck's constant times its frequency, the energy is linearly proportional to frequency. This is just a number, and it has to be equal to the difference between the energy levels of that atom. And every atom has different energy levels. Every type of element, I should say, every atom of each type of element has a unique set of energy levels. So carbon has one set of energy levels, hydrogen has a different set. And so the photons of light that atoms emit are different for every element on the periodic table. And this is a picture that shows that. So hydrogen is the simplest atom, one proton, one electron. It has the fewest number of orbits, and it emits light here and here and here and not elsewhere. Excuse me. Helium is more complicated. 2 protons, 2 neutrons, and 2 electrons. The neutrons don't do very much, but there are a lot more orbits. And you see all these different lines at which helium will emit or absorb light. And carbon is different again. And none of the these are 3 of the 92 elements on the periodic table. None of these elements has exactly the same spectrum as any of the other elements, because they all have different amounts of charge in their nuclei. So if we look at the light that's coming from a star, we can tell how much hydrogen there is and how much carbon there is by looking at the combination of wavelengths and how intense the different emission lines are. And we can do a precise chemical analysis and tell you whether the star has any carbon in it or not, for example. All stars have hydrogen, so that's not going to be a big surprise. And all stars have helium, so again, not a surprise, but they don't all have carbon. So we can tell if there's carbon, we can tell if there's oxygen, we can tell all the way down through iron. Now, this is really remarkable. And to show you how surprising this was, in the year 1842, the French philosopher Auguste Comte said, "There are things that mankind will never know." And that may be true, but in fact, he gave the example that mankind could never possibly figure out what the chemical composition of stars were. And when he said that in 1842, that seemed like a good guess, because how would you get to a star? How would you scoop up a piece of star? How would you get it back to the lab where you could do a chemical analysis? I mean, none of that made any sense in 1842. And so Auguste Comte seemed to be on solid ground with his declaration that this was a thing that mankind would never know. But within a couple decades, he was proven wrong. There may be things that mankind will never know, but the composition of stars is not one of them. So because the science of spectroscopy emerged within 2 decades, we were then able to analyze the light from the stars in the manner I described before and determine what is the exact chemical composition of all the objects that we can see in the heavens, including stars and galaxies. So the science of spectroscopy tells us not only what everything we see is made of, but as we'll describe in short order, it tells us also what is the state of motion of the things that we observe. And that is going to tell us how far away they are. It's a long story, but we're on the way. Any questions so far?
Yeah, let me throw one in. So returning to your lecture from a couple weeks ago. So a star is experiencing fusion. And
Yes.
the fusion process essentially changes the chemical composition of the star.
Yes.
And then as the star ages, its chemical composition changes. If I got, I
Yes.
think that's,
Yes.
okay.
Exactly.
So if a portion of the star ages and its chemical composition changes, and then it emits a light that is indicative of the new chemical. When that light comes out and displays that frequency spectrum you were just showing, is that chemical whose electrons have said gone to a lower energy state, has that chemical changed? In other words, it's no longer the original chemical.
Yes, the chemical composition changes. So there will always be a lot of hydrogen and a lot of helium. But what will change over time is that a relatively small number of those hydrogen and helium atoms will be cooked to make carbon and oxygen and nitrogen. So as the star ages, if you were watching the star over billions of years and doing spectroscopy the whole time, you would see the emergence of the lines of carbon. You would see the emergence of the lines of oxygen later, the emergence of the lines of silicon later, and finally, in the last stage, the emergence of the lines of iron. And since we aren't patient enough to wait billions of years, we just look at all the stars, and some of them are older than others. And so, we can see some stars have carbon, others don't. Some stars have carbon and oxygen and so forth. And the very most massive stars have iron also. So you can see stars at various stages in the evolution of the various stages of their evolution.
But when I see a star,
Yeah.
I see the spectra of light coming from it, which indicates that there's carbon, for instance, and it's emitting photons.
Yeah.
As the carbon emits its photons, is it no longer carbon? Does it degenerate?
No, it stays carbon because it is carbon because the nucleus has 6 protons. That's what makes it carbon.
Oh, so the
What
electrons
the
at the lower
electrons
state.
do doesn't change the type of atom.
Okay,
Changes the state of the electrons within the atom. And the atom will absorb energy from the surroundings, and so the electrons will go up to higher levels, and then they'll fall back to lower levels, emitting light. Then they'll absorb light, they'll emit light, and it's a continuous recycling.
okay, but once a carbon atom, always a carbon atom.
Well, until it fuses to make oxygen, yes.
Okay.
I mean, it's only in stars that's going to happen. So in the rest of the universe, if it's carbon, it's going to stay carbon. But if it's an atom within a star, it has the opportunity to fuse and make a bigger atom.
Okay, thank you.
It's all very wonderful, actually. And every bit of that is really essential to the existence of life. So it's not just idle curiosity. I mean, this is where we were, this is how we came to be. Okay, so the core of the topic that we want to talk about today is, as the old nursery rhyme said, twinkle, twinkle, little star, how I wonder where you are. So the question is that has perplexed astronomers for centuries is how far away is that twinkle, twinkle, little star in the sky? And we know we can measure angles very well. We can measure its position within the constellation or something relative to other stars with great accuracy, but we have great difficulty in measuring the distance. So we know that it's somewhere along this line that goes out to infinity, but just how long is the line to the star? That's the key question. And I wish I could tell you that we have developed a machine that we can point at a star and out comes a number and it says that star is 3 billion light years away. There is no such instrument. What we have developed is a bit of a kludge that solves the problem to some degree. It's not perfect and it's continually being improved, but it consists of a series of techniques. We have one technique that allows us to measure distance to stars that are very close. Then we have another technique that measures relative distances of stars that are further away. So this technique doesn't tell us the distance, but it says this one is 5 times further than this one. And if we can measure the distance to this one, then we know what 5 times further means. So if we lash these two ladders together, we are now getting out further. And there's another scheme and another scheme and another scheme. And all of these ladders represent techniques that give us the relative distance of stars within a certain range of distance from Earth. And if we lash all those together, then we get the distance all the way out to the edge of the universe. That's the strategy. We need to have a scheme to get further and further and further. And all of these schemes give us relative distances. This is 5 times closer than this, let's say, or this is 100 times closer than this. Only the first one actually gives you distances in miles or kilometers or some specific number. Okay, so this was the greatest challenge facing astronomy, and everyone worked on it to some degree. And the 3 most important people who made this ladder effective were Henrietta Leavitt and Edwin Hubble and Albert Einstein. Einstein provided the theoretical basis, and Henrietta and Edwin Hubble provided the observational backing, the data. So let's talk about, they have been over the course of time more than 30 different techniques that astronomers have used, excuse me, to enable them to estimate distance. And most of them were fairly terrible and had great uncertainties. The old joke in astronomy is if 2 astronomers measured the distance to a star and the values they came up with were differed by a factor of 10, one said it was 100 light years, the other said it was 1,000, then they would pat each other on the back and congratulate each other for measuring the right number. If they were within a factor of 10, they were happy, in other words. That's not what other people call good precision, but in astronomy, that was as good as you could get. Now, we're talking about distance measurements that are precise to, let's say, 5% or better. And the great thrust, a goal that people are aiming at is to get the precision distances measured to 1% or better. So astronomy has graduated from 100%, or I guess a factor of 10 is 1,000%, to 5%. And of course, we're never satisfied with anything less than perfection. And so we're looking for better and better. So there are 6 techniques that have stood up the test of time. And we use all 6 of these in sequence. The radar is for the nearest, and Kepler 1, 2, 3 laws for the next, and further away, and the furthest objects are identifiable only by their redshift. So we'll talk about each of these techniques, and we use them all lashed together to measure the distance to the edge of the universe. So let's talk about radar. That actually gives us a distance in meters or miles or whatever distance units you want. And the most important stepping stone to measuring further distances is to know the distance from Earth to the sun. So we do that by measuring the distance to Venus, Venus being in orange here. And Venus orbits the sun, of course, and it has a rather circular orbit, very low eccentricity. All planets orbit in ellipses, but the ellipse of Venus is very close to being circular. And if we measure its position at various times along its orbit, we can't see it over when it's behind the sun, but we can see enough of its orbit to calculate the rest of the orbit. And the sun is at one of the focal points of the ellipse. And since the orbit is almost completely circular, the 2 focal points are almost completely in the same position. So by measuring the distance to Venus, we can determine the distance to the sun. And we can measure the distance to Venus to plus or minus 100 feet, which is a precision of 10 decimal digits, which is fabulous. 1% would be 10 million miles. So this is vastly better than 1%. Well, that gets us only so far. Radar can't get to anything outside the solar system, and indeed we don't get good radar distance readings on even the most distant planets. So the next stage, having measured the distance from Earth to the sun, we can use Kepler's 1, 2, 3 law. And the 1, 2, 3 is a mnemonic that relates to the fact that if you have the mass m to the first power and the orbital period to the second power, that is proportionate equal to the radius of the orbit to the third power. That's 1, 2, 3 are the exponents. So you measure the mass of the central body in the case of the solar system, that is the sun. And if we applied this to something else, then we would measure the mass of that central gravitating body in multiples of the mass of our sun. M sun is the mass of our sun. The orbital period we measure in multiples of Earth's year, the period it takes Earth to go around the sun. And the orbital radius we measure again in multiples of Earth's orbital radius, which is called the astronomical unit. So if for the solar system, m is 1, and for Earth, t is 1 and r is 1. So obviously the Earth satisfies this equation, but so does Jupiter. So Jupiter has a orbit of 11 years. So that squared is 121. And the radius of its orbit is about 5 times the radius of Earth. And so 5 cubed is 125. And if I had used the exact numbers instead of 5 and 11, then it would be a perfect match. So by knowing the period of the orbit of a planet, which we can easily determine, then we know what its radius has to be to be in orbit around the sun. So we can measure with this technique, we can calculate the radius of the orbit of Jupiter, Saturn, Neptune, Uranus, and even Pluto, and even objects that are orbiting the sun further out than that, the Kuiper objects and so forth. Anything we can see and measure the orbital time, we can calculate the orbital radius. And in addition, we can use this law using a different m to measure the mass of galaxies and to measure the existence of dark matter. So this is a law that's useful throughout astronomy, not just to measure distances in the solar system. But measuring distances of the solar system is what we are focusing on today. Okay, the next step is parallax. And this is something that surveyors on Earth do all the time. This is how they measure distances across the surface of the planet. They have an instrument, which is basically like a telescope, and they look at something at a great distance that has a known length. So they have a standard ruler that the guy stands up with and on a pole, and it has the distance markings up and down the ruler. And so if you measure the angle from one end of the ruler to the other, and you know the length of the ruler, then by trigonometry, you know the length of this red line. So you just make a triangle and you calculate the tangent of the angle is the ratio of this to that. So that's easy to do. The other way to do parallax is actually what you and I do every day. And that is if we have two different viewing angles, like our eyes are separated by, let's say, 3 inches. If you know that distance between the eyes, and if you look at the angle that each of the line of sights has between them, then you can similarly calculate the distance away to the target. And this is what your brain does sort of automatically when you look around at the world outside. And it's the reason that you have 2 eyes. This is binocular vision. So your 2 eyes at different viewing angles, your brain determines the angle between, and it's not super high precision, but it's good enough so that you know how far away dinner is, and you have to, if you're trying to eat impala for dinner, then your spear has to hit at the right distance. So this is certainly an essential aspect of the survival of our species is our binocular vision. Okay, so we use that. First of all, before we get to how we use it, let's do a lab here. This is the only lab experiment that we can all do together by Zoom. So I want you to stare at all these letters on the screen and put up your finger about halfway in between, and then alternate looking at your finger with the one eye at a time, and observe the letters that are obscured by your finger when the left eye is open, and compare those to the letters that are obscured by your finger when the right eye's open. If you don't see the effect, then move your finger closer, and the effect will be bigger. So clearly, the finger blocks letters on this side when you're looking at the left eye, and it blocks letters on this side when you're looking at the right eye. So that's how your binocular vision works. Now we use that in astronomy. Is there anybody have trouble doing that? Okay, so we use this parallax in astronomy by using Earth's orbit. So Earth, the blue dot, orbits the sun. There's the sun, and it has an orbit of about 93 million miles radius. And so it's 93 million miles above the dotted line in January, and in July, it's 93 million miles below the dotted line. So if we're looking at a nearby star, then we can see this star from two different vantage points. It's binocular vision. We can't do it at the same time, but we can do it 6 months later, and the star doesn't move that much in 6 months. And so we can measure the angle in the sky between by using some distant star as a reference point. And then from this angle, we can determine the distance from the sun to the star by simple trigonometry. So you take the tangent of the angle and you divide Earth's orbital radius by that. And so Earth's orbital radius is this side of the triangle. And what you want to know is the base side of the triangle. And that's how you get it. And this works for nearby stars. And that gets us a step out further into the cosmos. And this is an example of using parallax on a much more distant object. So this is the first type, when you have one viewing angle and you have an object of a known size. So this was a supernova explosion. This is an image of a supernova explosion that occurred in 1987. And we are looking at it now 245 days after the original explosion. So we saw a bright flash of light on day one, and 245 days later, the Hubble Space Telescope took an image of the same part of the sky, and they saw this. And the gas that is brightly lit up is the gas that so the light from the supernova went out in all directions. And when it hit this ring of gas, that ring lit up brightly because it was illuminated by this intense light from the supernova. So we know that the radius of the ring is 245 light days. The speed of light times 245 days gives you the radius of the ring. And we measure this angle, which is very small. And so you divide 245 light days by this tangent of the angle, and you find out that the distance to that supernova is 168,000 light years. And that's measured with a precision of 2%. The 2% is the error on measuring the angle combined with the error on the size of the ring. But anyway, that's 2% is a very fine measurement. And this tells us the distance to the supernova, which is in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. So that gives us a distance to at least one of the points in the satellite galaxy. Okay, so parallax gets us farther away from the solar system, and even to the neighboring galaxy, satellite galaxies of the Milky Way. Now we come to standard candles, the technique called standard candles. And that is, if you have a light source of known intensity, then you can determine how far away it is by looking at how bright it appears to us. So this is how that works. You imagine you have a star, and just for fun, imagine that it's surrounded by a series of glass spheres of great size. So the photons that are coming out of the star in all directions, every photon is going to cross every one of these glass spheres sooner or later. And so the number of photons crossing each of the glass spheres is the same, but the surface area of the spheres gets larger and larger. So the surface area of the spheres grows as pi r squared. As the radius of the sphere gets bigger, the area of the sphere is 4 pi times the radius squared. And so since the number of photons is the same, then the intensity, the number of photons per square foot or whatever, per square centimeter, drops as 1/r squared. If we know how many photons are being emitted, we count on what the density of photons is where we are, then we will know what r is. So this is how you determine the distance to the star. As an example, imagine that you were looking at a housing development in which every house on the block had the same 1,000-watt light bulb on its porch. So the house that's next to you, one house away, and here's another light bulb that's 2 houses away and 3 houses away and 4 houses away and so forth. The distance squared is given on this middle line. And so if this looks like a 1,000-watt bulb 1 house away, the house that's 2 houses away will look like it's only a 250-watt bulb, because 2 squared is 4, and so on and so on. So if we measure what is the apparent brightness of this light source, and we know what the light source is actually emitting in its neighborhood, then we will know how far away it is. So the trick is to find things in the universe that we know how bright they are. That sounds like an impossible task. How do you know how bright a star is supposed to be? But that's where clever people came up with clever solutions. So if we know that the intrinsic brightness, then the brightness we observe in Earth is that intrinsic brightness divided by the distance squared. And we're going to measure the brightness of one star relative to a star that's closer. And so we will know their relative distance. We can't do this in a way that gives us the absolute number of kilometers away, but we can do this in a way that we can tell if something is 5 times further away than something else. And if we can measure the distance to that nearby thing with parallax, then we can calculate the distance to the further thing. That's the scheme. Okay, now variable stars are the key thing to employ, and stars can vary in intensity for a variety of reasons. Mostly they vary in intensity because their size changes, and some stars pulsate, and they cyclically, repeatedly expand and contract, and expand and contract. And when they're bigger, they have more surface area and they emit more light. It's not more complicated than that. Small stars emit less light than big stars. So the star it is unstable. It's alternately expanding and contracting. When it expands too much, it cools off and the pressure in the center drops and gravity forces it to contract. And when it contracts too much, then the pressure in the core becomes too high and it blows the star back out again. And so the star can, in these types of stars, can swing back and forth like a pendulum, like a weight on a string. They go back and forth as one effect dominates the other. And when it expands to maximum size, it is maximum intensity. So here is where Henrietta Leavitt made this enormous contribution. She always wanted to be an astronomer, but this was in the bad old days, about 1900. And she applied at Harvard to be part of the astronomy program, and they told her women can't be astronomers. And she didn't pay attention to them, and perhaps that was because she was deaf, so she couldn't hear these nasty things people said. But she was meticulous, and she discovered an amusing relationship between the intensity of a certain type of star and the period of oscillation of that variable star. And these particular types of stars are called Seyfert variable stars. Seyfert being the name of the first star that was discovered to have this property. And she was clever enough that she looked at Seyfert variables in other galaxies. This is the Large Magellanic Cloud. That's where the supernova that we talked about before occurred. This is the Small Magellanic Cloud. It's actually much smaller than the Large Magellanic Cloud. It just looks bigger on the photograph here. And the good thing about using a galaxy or some other object that contains a lot of stars is that almost all of these stars are about the same distance from Earth. So that eliminates the distance variable. If you can figure out the relationship between stars at the same distance, then you don't have to worry about the fact that the apparent differences in intensity are due to the fact that the stars aren't the same. So all of the stars in the Large Magellanic Cloud and the Small Magellanic Cloud are the same distance from Earth within a few percent. These are all different from these, but all of these stars are within a few percent of the same distance from Earth, and all of these stars are within a few percent of the same distance from Earth. So you eliminate the distance uncertainty by looking at these clusters of stars in the heavens. And what she discovered within the Large Magellanic Cloud and the Small Magellanic Cloud is there was, on a log-log plot, a linear relationship between how long it took the star to pulsate and how bright it was at its peak. So this is the plot. So if you know the distance to this star, then you know how bright the star is, and you can compare it to the brightness of this star as observed on Earth. And so you can calculate what is the distance to that Seyfert variable. And this is a modern image of a Seyfert variable in a different galaxy, M100, that's the name of the galaxy. And this is at its brightest, and this is at its dimmest. And so you see there's a dramatic shift in intensity. And if you figure out exactly how long it takes the star to go back and forth, then you can use Henrietta Leavitt's plot and figure out what is its maximum brightness. If you know its maximum brightness, you know how far away it is. And here is another example. This is important because this is a Seyfert variable star, and we're measuring its distance with parallax. So now we can use this to compare to Seyfert variables that are further away. This Seyfert variable star has a mass about 10 times the mass of our sun, and its brightness oscillates between 15,000 and 30,000 times the brightness of our sun. Super bright. And it takes about 41 days to do this. So the parallax comes in because every time the star gets super bright, it illuminates more brightly the gas surrounding the star. And so these are called light echoes. There's a pile of gas here, and when the star gets bright, this gets illuminated. This is another pile of gas that got illuminated the previous time the star got bright. And so we know this distance is 41 light days because it's a 41-day period. And so that distance is 41 days, and we measure the angle, the parallax angle, and we can calculate that this star is 6,500 light years away with a precision of just over 1%. So again, a very precise measurement, and this locks down the absolute brightness of the Seifets that we need for Henrietta's work. Okay, I'm sort of hurrying because we're running out of time. So if I go too fast, stop me. I won't stop myself. I can't do that. Now let's talk about redshift, which remember we discussed the fact that every type of atom on the periodic table emits a spectrum of different light frequencies. And now we can use that to see how that object is moving. Let's imagine that you have a star that emits only one frequency of light, yellow. And so if all of the light is being emitted by a single source, then you can imagine that these yellow lines are the crests of the waves, and the in between are the troughs of the waves. And if the star isn't moving, then all of these lines are concentric with the star. They are symmetrically surrounding the star. The center of every circle is at the center of the star, because that's where the light originated. But if the star is moving, then the circles are no longer concentric with where the star is. Each circle is concentric to where the star was when that light was emitted. This largest circle was emitted first. It's gone the furthest away from the star, and so it's centered at where the star was then. The inner circle is centered where the star is now, and the other circles are all in between. And so you see that as the star moves to the right, these waves are being squeezed together, and these waves are being stretched apart because the origin point isn't the same. Here, the origin point is always the same, so the waves are the same in all directions. But when the star moves, then the waves get compressed in the direction in which the star is moving, and they get stretched in the direction opposite to where the star is moving. Okay, so let's just focus on this midline. And here's the stationary star, and the wavelengths are the same on both sides. Here is the moving star moving to the right. These wavelengths were compressed, so the wavelength is shorter, the frequency is higher, and this looks more bluish than the yellow. Here, the wavelengths are stretched, the frequency is lower, and this looks more reddish than yellow. So red is the low frequency end of our visible spectrum, blue is a high frequency end of our visible spectrum, yellow is somewhere in the middle. And if we measure the amount of shift, we know where the lines are supposed to be if the star is not moving. We measure the amount of shift, we can measure the velocity that the star is moving. Now, that's the velocity that the star is moving either toward us or away from us. If it moves sideways, we don't see much difference. You can figure that out if you're looking over here then you don't see nearly as much difference as if you're on the same line as the velocity of the star. Okay, so red shift means the star is moving away from us. Blue shift means the star is moving toward us. So Edwin Hubble put all this together. He got Henrietta Leavitt's Seifert variable law, and he had the red shift going, and he used that to analyze stars in nearby galaxies, and he made this tremendous discovery. This is a picture of the Hubble Space Telescope named in his honor. And what he did was he examined Seifert variable stars, Henrietta Leavitt's favorites, in nearby galaxies, including this galaxy M31, which is the Andromeda galaxy. Before Hubble did this, this was just considered a blob of stars in our own Milky Way. And astronomers believed that the Milky Way was the entire universe, and so this was just a large collection of stars. And he looked at it and he found the distance to this object, and he discovered that this isn't just a large collection of stars that's part of our Milky Way. This is an immense collection of stars, even larger than our own Milky Way, and it is far more distant than ever any astronomer ever imagined before. In fact, it's 100 times further away than anyone believed it was before. And so overnight, the size of our universe grew by a factor of 1 million when this was discovered. And he discovered that the galaxies that are nearest us are moving away from us. The galaxies that are remote are all moving away from us. Henrietta Leavitt used Seifert variables as her standard candle. And nowadays we use a certain type of supernova explosion called a type 1A, which are also very regular in the amount of light they emit. They emit vastly more light than a Seifert variable, so that allows us to use this standard candle even further out. But it's the same logic as the Seifert variables. So Hubble made this plot. He plotted the distance to the galaxies determined by the Henrietta Leavitt Seifert variable rule. And so the distance would be vertical, and the velocity measured by the redshift, the velocity that the star is moving away from us, measured horizontally. The redshift is called z. So the distance is determined by the Seifert variables, and it corresponds to the yellow line. Anything on the yellow line is the same distance away, and anything on the red line is moving at the same velocity away from us. And so when he made this plot, one might imagine that he would have found dots all over the plot, that there would have been galaxies moving toward us at this distance and moving away from us, and their velocities wouldn't be related to their distances. They'd just all be some velocity at some distance. And this could have been the way our universe was. And if it didn't have a beginning, then that's probably the way it would be. But this is not what he actually saw. What he actually saw was all the galaxies that he measured are on a single line, that they all display the same relationship, that the redshift gets larger and larger. The velocity that they're moving away from us gets larger and larger as the distance away gets larger and larger. And this is Hubble's law. And so a galaxy that's 1 million light years away is likely to be moving away from us at 46,000 miles per hour. A galaxy that's 10 million light years away would be moving away from us at 460,000 miles per hour, 10 times as much. And this tells us something dramatic. Let me give you an example, a simple example from Earth. If this is a Seattle Space Needle and we're looking at cars leaving the city on a 3-day weekend, and we find out that all the vehicles on the road just happen to obey Hubble's law, that their velocities are linearly proportional to their distances, then imagine that we take this same situation, we photograph the situation, we make a movie of the situation, and now let's play the movie backwards. We would find that the sports car is coming back toward the Space Needle at 200 miles an hour. The van is coming back toward the Space Needle at 100 miles an hour. And they're both going to get here in 4 hours because they have this linear relationship. So this means, if you make the analogy now to the universe, if you have galaxies whose velocities of recession moving away from us are linearly proportional to their distances, then if you reverse that movie, all the galaxies will be in the same place at the same time. And that is the Big Bang. So a tremendous breakthrough realization. I'll give you another example. Different people understand things differently with different examples. So I give a couple. Imagine that you have a piece of elastic tape and you sew dimes, which are in yellow, to different parts of the tape. And you start off with these equally spaced dimes. Then we stretch the tape and we stretch the tape, and the dimes get further apart. And every dime, looking at the other dimes, would say that all the dimes are moving away from me, and they're moving away from me according to Hubble's law. A dime that's twice as far away will have twice as much stretchy tape, and so it'd be moving away from me twice as fast. If it's 4 times farther away, it'd be moving away 4 times as fast, and so forth. And it's not because any dime is the center of the universe, it's because all of them are moving away from each other at the prescribed linear relationship. And indeed, these galaxies come from all different directions in the sky. And so this expansion is uniform in all 3 dimensions of space, as well as we can determine. So the last step in measuring distances is, if we can measure the red shift of a galaxy, even if we can't measure anything else, then we can use this relationship to calculate its distance. So we just we make the measurement of its redshift, we go up to the line, we come across from the line horizontally along the green line, and where the green line intersects the vertical axis, that gives us the distance. And you see this works well up to a redshift of about 0.1. It turns out it's not completely linear. As you go to larger and larger redshifts, the galaxy that we saw from the James Webb Space Telescope was at Z12.5. So that is a lot further out than 0.1, 125 times further out. So we need to know exactly the shape of this curve at very distant distances, which is much more challenging, of course, and that's what people are working on now. Okay, so that was everything. Questions?
Yeah, Bob, can you hear me?
Yeah.
Okay. You brought up a number of things, kind of piggybacking on what I was trying to wrap my head around last week. So the question I have this week kind of relates to that idea of this, how galaxies kind of form. And when you did the thing with the Magellanic Clouds, it sparked my curiosity. I mean, what I remember that, didn't Hubble think that Andromeda was a nebula before he made the determination it was actually a separate galaxy?
Yes,
Didn't-
everybody made that assumption, including Hubble. Yeah.
So now, how do we, and don't we consider nebula part? They're not big enough to be like the birth of a galaxy is not from a nebula. Aren't they too small?
Usually the nebula are much smaller than galaxies. Yes.
So what are these, what's the difference between, let's say, a nebula and the clouds, the Magellanic Clouds? Why are they called clouds? Aren't they just galaxies?
Well,
Too?
when Magellan first observed them, of course, this was before Hubble. And so everything that was a fuzzy object in the sky was called a nebula, a cloud. A nebula is Latin for cloud. So, and they were distinguished from stars because the nebula were these fuzzy blobs. And some of those are still viewed as fuzzy blobs, the ones that are close, but some of them turned out to be galaxies. And the Magellanic Clouds are sort of in the middle. They're very small, they're dwarf galaxies. They have very few stars by comparison to the Milky Way and Andromeda. And they are not so far away, which is why we see them. If they were that small and they were really far away, we wouldn't see them.
So I guess where I was leading was leading to my question of kind of birth of galaxies. Do nebula accumulate to be large, to become larger and larger, and then ultimately become the basis for galaxies later? Or is that not the way to think about birth of galaxy?
Well, certainly I mean, our concept of the birth of a galaxy is that the universe began with a distribution of gas, which was almost entirely homogeneous. The cosmic microwave background radiation shows that when the universe was 379,000 years old, the most dense spots were only denser by about a few parts per 100,000. So the non-homogeneities were in the 5th decimal point. Everything else was pretty much the uniform. And then, you know, the parts that are a little more dense, they have a little more gravity than the neighboring parts. And so gradually those more dense parts suck particles in, and the less dense parts lose to their neighbors that are more dense, so they become sparser and sparser. And so this inhomogeneity increases over time. Now, we're talking about over billions of years, not in weeks or anything like that. And depending on the shape of the inhomogeneity and the neighbors and so on, that either proceeds rapidly or less rapidly, and it either makes something round or something, you know, of odd shape. And so you get this distribution of sizes and shapes. And the most dense things become spiral galaxies, and the less dense things become, either you call them star clusters or you call them nebula. Nebula is usually reserved for just gas that may be forming stars but isn't dominated by stars. Star clusters are a case in which the gas cloud has collapsed enough to form thousands of stars. So you see the brightness of all those thousands of stars. In the case of a gas cloud, you don't see it being bright in that sense. You see light that's reflected from nearby bright things. more than anything else. If you look in the infrared at very low energies, you might see the glow of the gas in the gas cloud, but that's at an extremely low level compared to a star. So you get this complete distribution, and you know, we draw lines and we call these nebula, and we call these dwarf galaxies, and we call these big galaxies. So, but those lines are human creations. Nature doesn't obey those lines. So there's the whole continuous distribution of these collections of stars. And the biggest, brightest ones are the elliptical galaxies that are the oldest and had the most time to suck things in. And they sort of are giant blobs of trillions of stars.
So that discovery from JWST, is that actually now considered the oldest?
I think it is.
Let's see. Yeah, go ahead.
I think it is. There isn't one that's much older than that. I mean, this is very early on, 350 million years after the Big Bang.
Right, right. So it's, yeah, okay.
And it's a very distinct signal. Often you get a signal that's marginal when you're looking at the furthest thing, or the most extreme case, you get a marginal signal. That's because if it had been a bigger signal, someone would have seen it before. And that signal from the James Webb is very distinct. I mean, that spike that we saw in the first slide, that looks like a tower. I mean, it's just a vertical line. It sticks out from the data without any possible question that that's a specific measurement.
Right. Which means that it's not going anywhere. If it's that old, it's not dying. In other words, it's not.
It's probably forming. Yes, it's probably in the birth stages. Yeah. And you know, if we get 100 more pictures like that, we will find one that's older, and we will find a distribution, and some theorists will put that together, and they will, they'll use a supercomputer to simulate how the formation occurs, and they'll tweak their model until they match the data, and we will learn something. And it'll probably be very important, but we need a lot of data. You know, one galaxy isn't enough. We may need 100 or 1,000, and we will need to analyze and come up with models that explain what the data that we observe means.
Right.
Yeah.
Okay. Thanks. Thank you.
It's going to be fun for 20 years. Anything else, guys? Okay, next session will be a week from today. And we're going to talk about, let's see, I think week 4 is black holes and neutron stars and the stellar remnants. And then week 5 will be dark matter and dark energy. And we'll wrap up put together all of this in our theory of cosmology in week 6. So thank you all very much, and we'll see you next time.
Okay, thank you. Thanks.
Thank you.
Thanks.